Now start. So the idea is explained that given two objects in an infinite category, the connection between that two objects in an infinity category is a Kan complex. Okay, so we will remember the following: the homotopy hypothesis. Okay, infinity groupoids are equivalent to topological spaces. Okay, that is the homotopy hypothesis. So Kan complexes can be seen as an infinite groupoid. So when we think in a Kan complex, we also think in a topological space in a weak homotopy way. Okay. So we will start with the classical case. When we have a category, the definition of a category says that given two objects, the morphism between that object is a set. Okay, so what means that when we consider the ordinary nerve of a category, we study two levels. The level 1 is the morphism of the category, and the level 0 are the objects of the category. So when we apply D1 to a morphism in level 1, give us the domain of the morphism. Okay, and when we apply D0 to the morphism, that gives the codomain of the arrow. Okay, so we need to reformulate this to construct a diagram, and in that way we can construct the set of morphisms between two objects in a category. So consider 1, the category with two objects and a unique arrow. Okay, so a morphism in a category is just a map from the category with one object to the set homomorphism of the category. Okay, so what means this? This set we can rewrite it in the following way. It's just all the possible morphisms in the category of sets from the ordinary nerve of the one category. Okay, at level 1. Okay, we have to remember this is a point. It's just a point because this category only have one arrow. Okay, to the ordinary nerve of the category C at level 1. Okay, so this means are all the possible morphisms between the set with one point to the set of morphisms. That is equal to the set of the morphisms of the category C. Okay, so if we want to extract the domain and the codomain of the arrow, we only apply D1 and D0. Okay, so this construction is the same as this diagram. Okay, now we did only for one arrow. If we want to do for all the possible arrows from X to Y, we have to consider the following diagram, the red box. So if we take the pullback, we have that the pullback is the home set from X to I. Okay, so please remember this number 1. Okay, so this is the basic idea. How can construct the set of morphisms as a pullback. Okay, now we have some problems when we try to study the mapping space in an infinity way. Why? Because it's easy to take a pullback in the category of sets. Okay? But now the problem is how can construct a diagram that encodes the notion of relation between two objects in an infinite category. Okay? So the first problem is what model do we choose? Because we have the model of Leary, the model of Rex, and we have also model category. And also in which category do we take the pullback? Okay, so we have some problems. Okay, we have different approaches to solve this problem. One is Duggar and Spivak, but they work in model enriched categories. Okay, and today I don't explain that notion. The notion of Leary I will explain at the end of the talk because it's a different approach that I will explain today. Okay, the approach that I will explain is the Rex approach. Okay, other approach is the real and variety, but the idea is the same of the idea of Rex. Okay, so any question at this point? Comment or suggestion? Or can I continue? So I suppose that everybody is agreed that I can continue. So we start with some terminology. Okay, so we have to remember that delta n is the simplicial set defined by the formula, the red formula. Okay, this means just that is the representable functor of the finite ordinal n. Okay, we also have to remember that when we think in a level n of a simplicial set, the red circle, is just all the possible morphisms between the delta n to x. Okay. Other stuff we have to remember also too is that the boundary of delta 1 is isomorphic to delta 0 product delta 0. Okay. So it's just remember some stuff that Thomas explained in the previous talks. Next one. We will use this definition in a special case. So let C be an infinite category. The functor category is described by the simplicial set of all the possible maps from the simplicial set K to C. Okay, so the proposition is the following. Let K be an arbitrary simplicial set. For every infinity category C, the simplicial set of functor from K to C is an infinity category. Okay, so we will use the following case when K is equal to delta 1. Okay, this means the following, that the functor from delta 1 to C is an infinity category. We will use this case, okay? K equal to delta 1. Okay, why we need this proposition? Because to define the mapping space, we have to construct a diagram, but this diagram is the same as the classical case. Okay, all the possible functor from delta 1 to x. Okay, if we remember in the classical case, we have that is the home in sets from the nerve of the one category to C. Okay, so in this case, we take the pullback in the category of simplicial sets, and we change the ordinary NER for some enriched category, and that enriched category is delta 1. Okay, but the idea is the same idea. Okay, any question at this point? So we take the pullback of this diagram, and that gives a simplicial set. At this point, we only know that this is a simplicial set. Why? Because each of the elements of the diagram lives in simplicial sets. Okay, I know are infinity categories, but we take the pullback inside of the category of simplicial set. So at this point, we have different ways to approaches to the mapping space. One is construct a pullback inside the category of simplicial set. The Lewis approach is take the pullback inside the homotopy category or over the slide or co-slice of the infinity category, but I will explain this after. Okay, so at this point we only construct a simplicial set. Any question at this point? Well, I will continue. Okay, so in the literature, it's usual found that the people don't write the functor category from the boundary delta 1 to x. They prefer write the following product. Okay, but that happened because we have this isomorphism. Okay, the blue box. And other observation is easy, that when x is the ordinary NER of a category, we have that the pullback 1 is equal to the pullback 2.
Wilson?
Yes, sure.
Sorry, just a minor thing. I think maybe it's a typo, but the boundary of delta 1 is the co-product of delta 0 with delta 0, right? Or am I mistaken?
Yeah. That's right. So you have that. Okay, but when you have this one, it's the same with this stuff, but this is isomorphic to x. It's a little tricky.
No, what I mean is instead of the product, you have the co-product. So it's a disjoint union. The boundary is a disjoint union of delta 0 with itself.
Yes, but when you apply the functor category, that disjoint union go to a product.
Yes, that would be why you have x times x.
Yes.
But to the left of that, you have there should be the co-product, right? Not the product.
This one.
Yes.
Thanks, Thomas. It was a mistake, I think so. But I think so is the product. I don't know. I have to check that. I don't know if the is the product or the co-product.
Well, I think you just explained it, right? It's the co-product, and when you apply it on the home, it turns it into a product.
Yes.
Okay. Yeah, that's it.
Okay.
Thank you.
No, to you. So I will continue. Okay, but we think only take two objects, but if we were in infinity categories, we have the option to take the pullback along any objects. So in other words, we can repeat the same construction, but now we take n objects. Okay, so we change the delta 1 for delta n and repeat the same construction. Okay. And again, this pullback is a simplicial set. But now, why do we say mapping space? Okay. We have to remember the first slide, That is the homotopy hypothesis that infinite groupoid is the same as topological space, and can complex can be seen as an infinite groupoid. So we have to prove that that simplicial set of the connection between x to y in an infinity category is a Kan complex. And that is the reason we describe this object as a mapping space. Okay, but how can do that? We have to use the following lemma. Let C be an infinity category and let J be a monomorphism, which is a bijection on vertices. Then the fibers are Kan complex. Okay. So let's see via an infinity category contain a pair of objects x and I. The simplicial set is a Kan complex. But why happened this one? Well, we have to remember that we have a inclusion between the boundary of delta 1 to delta 1. Okay, so that induces a monomorphism that we call J, for example, in this case, from the boundary of delta 1 to delta 1. Okay, so we have that the functor applying this lemma from delta 1 to C the fibers of this stuff are Kan complex, no? Okay, but what are these fibers? Pues we only have to take an object in this category, but take an object, we can take a pair, and for delta 1 to C. So when we take the pullback, we have that pullback is a Kan complex applying the lemma. Okay, that is the reason why when we talk about connection between two objects in an infinity category, we think in a mapping space or in a Kan complex. Okay? Any question at this point? Or everything is clear? Well, I would suppose that everybody understands. So, in the classical case, when we have two morphisms, we have that there exists a unique arrow that encodes the composition of two morphisms. Okay, but in an infinity category, that is more complicated because we have many options to describe the composition of two morphisms in an infinity category. So we have to construct a nice way to encode the composition in an infinity category. But for that, we need a lot of terminology and some technical results. So if somebody has a question in any point of the notions of definition, let me know it, please. So we start with the first one, right lifting property. So suppose we have a category, a classical category, and let P and Q two morphisms in that category. So P is said to have the left lifting property with respect to Q, and Q the right lifting property with respect to P. If given any diagram of this form, there exists a dotted arrow as indicate regarding that the diagram commutative. Okay, this means just we can find a solution of the square. A solution is just a map, a lifting, that satisfies the two triangles commutes. Okay, so it's just a notion. Now, more definitions. A morphism F of simplicial set is a trivial figuration if F has the right lifting property with respect to every inclusion from the boundary of delta n to delta n. So in other words, it's just the following. This is the inclusion. We have x to s f. Suppose we have arrows, so we can find a blue dotted arrow. Okay, that is a trivial figuration for each n. Okay. Now, what is an inner vibration? If F has the right lifting property with respect to all or inclusions. In other words, this diagram. Okay. Now, other notion is inner anodyne. A morphism G is inner anodyne if G has the left lifting property with respect to all inner vibrations. Okay, so this is just terminology, some construction we need. Now we need a key point of the proof of the composition law in an infinite category is the following. If I is inner anodyne and P is an inner vibration, then this morphism R is a trivial vibration. But what is R? No? So we have that a map from B to I is here, the mapping from B to I, and we have a map A to X. Okay, so the symbol I upper trig means precompose with I. Why? Because if we have B to I, we just precompose with I. Okay, now if we have A to X, P lower trig means post-compose. So what means this? Well, it's just AX and after we apply P. Okay, so this lives in the mapping from A to I. Okay, now we have the mapping space from B to X, for example. So it's a natural way go to the mapping space from B to Y. In this case, it's just precompose, post-compose with P. This means the following is P X and after apply P. Okay, the lower part now the mapping space from A to X. So the idea is just precompose. Sorry, precompose with I. Okay, so what means this? That the outer diagram commutes. Okay, so if we take the pullback of this diagram, we have this object, the red box. Okay, so since this is a pullback, there exists a unique arrow from the map from B to X to the pullback. Okay, and that is R. It's a little technical, but I hope everybody understands the idea. Okay, any question at this point? No, I don't think so. So I continue with the next one. Okay, now more terminology. The spine of the n-simplex delta n is the simplicial subset In of delta n spanned by non-degenerate one simplexes from 1 to n carrying 0 to I and 1 to I plus 1. Okay, so in other words, is the following. For example, for I2 in delta 2, it's just the simplest generated by 0 to 1 and 1 to 2. Okay, that is I2. For example, I3. So it's just spanned by no degenerate one simplex. So 0, 1, the first one, 1, 2, and after 3. Okay, this is I3. And this is inside of delta 3 because a picture of delta 3 is this one. Okay. Any question in this definition? So please remember the following notation. The long edge of delta 2 we will denote as delta 2 upper 0, 2. Okay, so that is the long edge. So please remember the notion, the notation. Now we start with the important thing of the talk. Construct the composition inside an infinity category. Okay, so we have to use the following lemma. The spine inclusion in to delta n are inner anodyne for all n. So let C be an infinity category. Let I be the canonical inclusion. And let P the unique map from C to the terminal simplest set 1. Since the canonical inclusion is inner anodyne by the previous lemma, and P is an inner fibration that since C is an infinite category. Okay, so P is an inner fibration since C is an infinity category. So we can apply the last proposition, the tricky proposition. And what say that proposition? We have that R is a trivial fibration. But why we need this one? Well, be the following lemma. Every trivial formation admits a section. So since R is a trivial fibration by the previous lemma, R admits a section S, so we get the diagram, this diagram. Okay, what means that we can go from this functor category and after apply R prime and we go to this object. Okay, so a picture of what happened in this point is the following. Suppose we start with this, for example, AB. So S what do sends this diagram to a 2 simplex inside the category. Remember, we have many options. So, but the section fixed one, for example, .dg2, for example, and AB. So this is sigma. This lives in this functor category, right? And what do R prime? Where R prime just restrict this sigma 2 and extract the possible composition. What means if G2. Okay, so this composition can be thought of as a kind of composition functor. Okay, but again, that section chooses some possible composition. That is the reason we think a possible. I use the possible word. Any question at this point? Everything was clear? I suppose yes, so I continue. Now, the previous construction was a general construction. Now we need to do the same, but only take 3 objects inside the category C. So the lemma says that take 3 objects and restrict that construction, and that construction again is a trivial figuration. And we can apply again the same arguments to construct a section of G2. Okay, and we have that section compose the R prime. This span of G2 gives a composition. Okay, but remember, we have to choose one possible composition. Why? Because if we have this diagram, we have 3 objects, x0, x2. We have many possible arrows. So we have to pick one, for example, G2. Okay, so this composition depends of the choice of the lifting. Okay, so we have many possible composition functor. Different of the notion of category theory that the composition is unique. Okay, now the natural question is this composition associative? The answer is yes, but natural isomorphic. That means the following diagram commutes.
Sorry, Wilson?
Yes?
I didn't get the connection. Could you explain again where G2 came from on the last slide?
Okay. When you have 3 objects in an infinite category, for example, I will create a new word here. Okay, sorry, I suppose we have x0, x1, x2. Okay, 3 objects, right? So you know that you have 2 maps, A and B. Okay, since C is an infinity category, we have many options of lifting, right? Okay, so you have to choose one because you have to restrict this spine. Okay, so you have different ways to go from A, B. So this is in delta, for example, delta 1, sorry, I2 to delta 2, right? Because here are 2 simplex. Okay, yeah. But what you choose, what lifting you choose? You have to choose one that I called G2.
Yeah, okay? That I understand. Could you maybe go back to the previous slide, please?
Sure.
And to the one before that. Okay. So the mapping space of 3 objects, that would also be defined as some kind of that would be a pullback again, right?
Yes.
And that can be thought of as the same thing as the somehow the set of those one
Technical
vertices.
is the
Sorry?
following. The technical definition is the following. Suppose you have this one, you take the boundary of this one, okay, and you pick an object. What object? x0, x1, x2, okay? That gives the mapping space from x0, x1, x2. This means are the possible two simplex that initial object is x0, after go to x1 and after go to x2 at level 0, okay? Is the possible two simplex. At level 3 is the same step, but you construct a trig simplex. Okay, an example could be the following. For example. Yes?
Okay. Okay, I think that's good enough for me for now. I guess the details, we'll check them later.
Yes, but that is the reason we have to fix some possible composition, because
that
we
I
have many.
understand. Yeah.
Okay, so
yeah, thank you.
don't worry. Okay, but as I said before, we have different approaches to construct the mapping space. Other alternative is the following. Construct the mapping space inside the category, because we construct the previous construction was inside the category of simplicial set, and using some conditions, some property, and some construction, we can deduce that the mapping space in fact is a can complex, right? Now we want to do inside the category. So how can do that? We take the co-slice category of C over a point X, and we have a forget functor. If somebody don't know what is this category, just think at level 0 is all the arrows that the domain is X, and level 2 is the two simplex that the first point is X, and so on. Okay, so the forget functor phi, well, forget what? Forget X. Okay, so we have this diagram. When we take the pullback, we have the left mapping space. At the same way, we can do this construction, but over the codomain of the arrow. That means the right mapping space. Again, this slice category is a level 0 is all the morphisms that ends in Y. Level 2 is the, sorry, I was a mistake in this point, are the two simplest that end in Y, and so on. And again, the forget functor forgot what? Y. Okay? That is the idea. So we have a diagram, and we take the pullback of that diagram. So that this is the right mapping space. Well, we have canonical inclusion between each of these possible models of the mapping space, and we have that all the possible alternatives are homotopy equivalents of can complexes. And for us is enough, because working infinite category, the idea is everything is homotopy equivalent. And for us is enough. Okay, but the proof is a little tricky, so I omit exercise for everybody and myself also. Give an example of an infinity category shows that the three different approaches are not isomorphic to one another. Okay? And that's all. Any question?
So thank you, Wilson. Is any question?
I hope everybody can listen me okay.
So,
I don't know if
thank you, Wilson. Please you mute yourself to give thanks to Wilson, and that's all.
Thank you, Wilson.
thanks to everybody. I don't know if somebody has a question, suggestion.
I have a question, but it's just I think philosophy. Can you go back to the definition of the? I think it's a proposition when you have a big diagram.
I know what this proposition.
This one. Yes, you are making this to define the composition, I think. But if you don't have a composition, how you define the pre-compose with I or post-compose with P if you haven't?
No, because at this point, well, I know I use of notation with map, but we have to remember that A and B are simplicial sets. Okay, and we work inside the category of simplicial sets, and that is a category. So when we talk of I is inner anodyne, but we have to remember our simplicial sets. So it's a simplicial map, and the composition of simplicial map is well defined. That is the reason I can pre-compose or post-compose, because at this point we work inside the category of simplicial sets.
Okay.
Okay, so this is okay. Another question?
So if there's no question, we will see you the next week, I think.
Yes.
At the same time.
Thanks to everybody.
Thank you. Bye-bye.